So for today, we're going to talk about integration by U-substitution. Okay, this is a part of our study in integral calculus. And basically, we're going to solve 10 problems in order for us to master this topic of U-substitution. So U-substitution, from the word itself, is that we're going to substitute some certain variable, the u, in the equation of the integral in order for us to evaluate the integral. So we need the knowledge of differentiating in this topic. So basic differentiation. So again, we're going to substitute u, okay, the variable u in our equation and solve the integral in a very simple way using power rule or using some of the integration formulas. So let's get started. So the first one is that we have the integral of 2t cubed plus 1 all over quantity t raised to 4 plus 2t raised to 3 dt. So the very first thing that we're going to do here in U substitution is that we know that the integral is can be solvable in U substitution if we let some variable u, okay, here in our equation. In this case, it's either we're going to let u the 2t cubed plus 1 or the t raised to 4 plus 2t. Okay? So, and we're going to let u and we're going to get the derivative of that u with respect to the variable t. Okay? So, the most appropriate u in this example is that we must get t raised to 4 plus 2t, excluding, of course, the exponent. Okay? So that, okay, if we get the derivative, okay, of this u with respect to t, we're going to get 4t cubed plus 2 with respect, of course, to dt. And if we are going to factor out 2 here, so we have 2t cubed plus 1 dt. As you can see, this portion of our du is the numerator of our integral. Okay? So, sir, we have 2 here. So, there's no problem. Okay? So, we can divide both sides by 2 to eliminate that 2 here, leaving this right side of the equation. We have 2t cubed plus 1 dt, which is entirely this. Okay? So, and this denominator, t raised to 4 plus 2t, we let this as our u. So now we can perform our u substitution. So what will happen? So we know that this 2t2 cubed plus 1 dt is now equal or equals du all over 2. So we have the integral of du all over 2. That is this term, okay? Because we substituted it on the integral. Du all over 2, all over, okay, we let u this term. So we have u raised to 3 because this is raised to 3. Okay, that's the very reason why we didn't include the raised to 3, because if we include the raised to 3, okay, so what will happen is that the du will be different. Okay? So, now, by rules of integration, this can be simplified as du all over 2 multiplied by 1 raised to 1 all over u raised to 3. So, by principle of basic integration techniques, we can factor out 1/2 outside of the integral sign because that is a constant. So, we have du all over u cubed. As you can see, it's very much pretty easy. This integral is pretty easy to evaluate because we will be needing power rule only. So we have 1/2. I can raise this into a negative exponent. Okay, if I want that to be in the in the numerator, so this becomes negative exponent. Okay, that's the rule, the exponential rule. Whenever we get the reciprocal of this, we negate the exponent. So we have u raised to negative 3 du. And of course, by power rule, okay, This is very basics. So we can now integrate this. So we have 1/2. That would be, this would be plus 1. So we have u raised to negative 2 all over negative 2. Okay, and then plus c. So simplify, what we have numerator times numerator, that's u raised to negative 2 all over 2 times negative 2, that's negative 4 plus c. But again, take note that our original variable is not in terms of u, but in terms of t. So we have to convert this u back to its original variable. So we have u equals t raised to 4 plus 2t. So we're going to replace the value of u by this term. So now we have t raised to 4 plus 2t raised to negative 2 all over negative 4 plus c. So this could be our answer, or we can put this down. Okay, so we have negative 1 all over 4. If we put this down, okay, we will negate the exponent. So we have t raised to 4 plus 2t squared, okay, plus c. And this should be our final answer for this problem number 1. So it takes practice in order for us to recognize that the given integral is U-substitution. So it takes practice. So as long as we can choose a suitable U, and if we differentiate that, the corresponding differentiation of that U is present in the integral, then we can use the U-substitution. So another example is this. Oops. Another example is this. For number 2, we have to get the integral of 3 all over 5y plus 4. We have dy. Okay. So, the very first thing that we're going to do here is that we must let u equals 5y plus 4. So that if we get the derivative of that u with respect to y, because we have a variable y here, that would be 5 dy. Okay? So, we have an available 3 dy here. But of course, we know, okay, that we can rewrite this integral, okay, by what? Factoring out this constant. So it's valid that we factor out that constant because that is a constant. So we have dy all over 5y plus 4. So all in the numerator, all we have left is the dy. And we can express our du in terms of dy. So by dividing both sides by 5. So we have du all over 5 and then equals dy. So now we can perform the u substitution because we get the dy, which is equal to du all over 5, and then we have let this denominator equal to u. So we have 3 integral of du all over 5 all over u. Okay, this is u. Dy is equal to du all over 5. So again, we can factor out this 5. Okay, so rewriting this integral, it would become d all over 5 multiplied by 1 all over u. Okay, that's the rule. We reciprocal the denominator, we reciprocate the denominator and proceed to multiplication so that you will not be confused. So we have 3/5. I can factor out the 1/5 here so that I have integral of du all over u. So I factor out 1/5 here. Okay, so this becomes 3/5. So we have du integral of du all over u. That is simply what? Ln of the absolute value of u plus c. Okay, this the integral of du all over u is ln absolute value of u plus c. But u again is equals 5y plus 4. So we have to substitute it back to our original variable. So we have 3/5. This should be 3/5 ln of the absolute value of 5y plus 4 plus c. So this should be our final answer for this problem. Pretty easy, right? So, yeah. Okay, let's proceed with another Example. So we have number 3. We have the integral of 3 quantity. We have 8y minus 1 multiplied by e raised to 4y squared minus y dy. Okay. So in first glance of this problem, you might find it complicated, but actually it's not complicated. If you know the U-substitution, if you're going to carefully observe the given integral, okay, we have e raised to 4y squared minus y here. Okay? But if we try to get the derivative here mentally, okay, this is 8y minus 1, which is actually this one. This one. Okay? If we try to differentiate this. Okay? So, now, before anything else, these three terms are actually multiplied. No? So we have 1, 2, 3, 4. These three things are all in multiplication. So I can factor out 3 outside of the integral sign. So that this becomes 8y minus 1 e raised to 4y squared minus y, and we have dy. So obviously, we already know what substitution or what u are we going to use? Let me write that in red. So we have u equals 4y squared minus y. So that if I get the derivative of u with respect to y, that would be 8y minus 1. Okay? With respect to y. That's why we have a dy here. Which is actually this 8y minus 1 and dy here. So if we are going to carefully rearrange, okay, our given, we put this first, then we have 8y minus 1 dy, we can see that this term is actually equal to du. Okay? So, and of course, this 4y squared, we let that as our u. So, it's now time to substitute this. So, we have 3 integral of e. Okay, we have 4y squared minus y. We let that as our u. So this becomes raised to u. And then this 8y minus 1 dy is now our du. So the seemingly complicated integral is very easy because of u substitution. So we have 3. The integral of e raised to u doesn't matter. That's e raised to u still plus c. But we need to substitute back the value of u, and that would be 3a raised to 4y squared minus y plus c. So this should be our final answer. So it's not that difficult, okay, if we just know how to choose the appropriate u and du. Okay? So for number 4, we have to get the integral of x squared quantity 3 minus 10x cubed raised to 4 dx. Okay? So still, this is a u substitution. Okay? We have to carefully select our u here. It's either this one or this one inside the parenthesis. So we can use the u here, because if we evaluate the derivative of this x cubed will result into an x squared, which is available on the integral also. So if I let 3 minus 10x cubed as my u and get the derivative of this, so this is a constant, so this would be 0. So power rule, by differentiation, this would be negative 30x squared dx. So in other words, I have du negative 30x squared dx, but I have x squared dx here. Okay, so I'm expressing this right side of the equation as x squared dx only. So I have to divide both sides by negative 30. So we have du all over negative 30, and I have x squared dx here. And Viola, we can now perform u substitution. So again, rewriting the integral, I have 3 minus 10x cubed raised to 4, and I have x squared dx here. This x squared dx here is equivalent to du all over negative 30. And this inside quantity here, 3 minus 10x cubed, equals the u. So I can now integrate. Okay, that would be u raised to 4. This entire 3 minus 10x cubed, we left that as a u, so that we have u raised to 4. And then we have x squared dx, and that is equal to du all over negative 30. Okay, and again, the rule is we can factor this outside, negative 1 all over 30, and then we have u raised to 4, we have du, and this is power rule. So we have negative 1 all over 30, and then we have u raised to 5 all over 5 plus c. And again, if we simplify this, negative 1 all over 30 times 5, that's negative 1 all over 150. And then we have u raised to 5. But again, we need to substitute it back to its original variable. So we have this u raised to 5 becomes 3 minus 10x cubed raised to 5 plus c. And this should be our final answer for this problem. Okay, so another problem involving uh, transcendental function, trigonometric function. So this would be our number 5, integral of 1 minus 1 all over w, okay, cosine of w minus ln of w, then we have dw. Okay, so in integrals, in evaluating integrals, it's not always x, it's not always y. So we can have different variables such as this example. So we have w as our variable. Okay, so how do we perform u substitution here? Okay, so what will be our u? We have two choices. Is it this or this one? Okay, but it is seemingly that if we choose this inside function of the cosine as our u, this will be the result. Why? Because if we get w minus ln w, if we differentiate this with respect to w, that would be 1 minus 1 all over w, which is this. So we have u, okay, w minus ln of w. So we can differentiate u with respect to w. That would be 1 minus, if we differentiate ln, that is du all over u. So the derivative of w with respect to w, that would be 1 all over itself. Okay, 1 minus 1 all over w. And of course, don't forget the dw here. So as you can see, now our integral, we can rewrite this as cosine of w minus ln of w. And then we have 1 minus 1 all over w dw. As you can see that this function is equal to our du, equals our du. And this one inside function of the cosine equals u because of our u substitution. So we can now perform the u substitution. So again, we have the integral of the cosine of w minus ln w equals u. And then we have, of course, that's equivalent to du. This whole term is equivalent to du. Okay, so what will happen? Cosine, integral of cosine. Okay, integral of cosine will be, of course, sine of u. Okay, this is u, not w. So sine of u plus c. Okay, but we need to substitute it back to its original variable so that, okay, that is now sine of the u, which is w minus ln of w plus c. So this would be our, should be our answer for number 5. Okay. Okay, let's go now to another example. For number 6, that is number 6. So we have the integral of sine of 1 minus x multiplied by the quantity 2 minus cosine of 1 minus x quantity raised to 4. Then we have dx. So this could be a little bit tricky, okay? But we know that we have a cos sign here and we have a sign here. So the very best choice that we can make is that we could let u, okay, we can let u equals this. So not including the raised to 4. So we have 2 minus cosine 1 minus x. What is the reason for that? Is because if we get the derivative of this would be 0 minus derivative of cosine would be negative sine copy the 1 minus x, okay? And of course, the differentiate the inside function. This is chain rule, of course. So 1 minus x, differentiate this with respect to x, that would be negative 1. And we have dx here. So rewriting that, so we have negative times negative would be positive times the negative 1, that should be still negative sine 1 minus x dx. And as you can see, we have sine of 1 minus x, and then we have dx. No need to worry about the negatives. So we can multiply this by both by negative 1 so that this becomes negative du, and when we have sine 1 minus x dx. So now we have sine of 1 minus x dx. So now we can proceed with the u substitution. So we have integral, okay? Integral, of course, we represent this 2 minus cosine of 1 minus x as our u. So that would be u raised to 4. Okay? So because of the 4 here. Then, of course, we have sine of 1 minus x dx. This is that term. So we have negative du. Okay? So we can factor out the negative outside of the integral sign so that we don't have any problems. So if we evaluate this would be u raised to 5 all over 5 plus c. And of course, we need to substitute it back to its original variable, which is x. So we have u. Our u is, I can separate this. So we have negative 1/5. Okay, that is still the same. Multiplied by our u. So that would be, our u is 2 minus cosine of 1 minus x raised to 5 plus c. So this should be our answer in evaluating this integral. Okay? Okay, let's try another one with a radical. So we have number 6. Later on, we'll try to solve some more transcendental functions. Integral of x all over square root of 1 minus 4x squared dx. Okay? So it does have an integral or a radical here. So what are we going to do is that we can let u, okay? So we have x dx on the numerator. So we can let u as 1 minus 4x squared, okay? And the derivative of that would be 0 minus 8x dx. So du equals negative 8x dx. So as you can see in the numerator, okay, we have x dx. So I can express this in terms of x dx only by dividing this both sides by negative 8. So we have du all over negative 8 and we have x dx. So now we can perform the u substitution. So we have x dx on our numerator. Let me just rewrite 1 minus 4x squared here. So this would be equal, this will be equal to, okay, the integral of the x dx, which is du all over negative 8 all over the square root of 1 minus 4x squared, of which that is our u. So I can factor out the negative 1 all over 8 outside of the integral sign. And then we have du all over square root of u. Okay? And if we express the square root of u in terms of exponents, so we know that square root would be du all over u raised to 1/2. By power rule, I can reciprocate this, get the reciprocal of this, but we will be negating the exponent. So we have negative 1 over 1 1/8, integral of u raised to negative 1/2, then we have du here. So, Viola, we can get, or we can simply evaluate the integral of this using the power rule. So we have u raised to negative 1/2 plus 1. So that becomes u raised to 1/2 all over 1/2, of course, plus c. So we know that upon simplifying this, so we have u raised to 1/2, okay, this would be u raised to 1/2. Simplifying this would be u raised to 1/2 multiplied by 2 all over 1 because we get a reciprocal of the denominator. Okay? Just for you to clarify. So we have 2 times 1. So negative 2 all over 8. We have u raised to 1/2 plus c. We can express this in lowest term. We have negative 1/4 u raised to 1/2 plus c. But okay, we are done integrating, but we need to what? Substitute the u back to its original variable. So we have negative 1 all over 4. And then, what is our u? Our u is 1 minus 4x squared. 1 minus 4x squared raised to 1/2 plus c. This can be the answer. Okay? Or we can express this 1/2 in terms of its square root. So, this is another possible answer if we are going to express our answer in terms of its radicals. Okay, let's go now to problem number 7, I think. This is problem number 7. Okay, this is problem number 7, not 6, because we have already problem number 6 here. So, problem number 8. Okay. Let me just rewrite this. Problem number 8. So, for problem number 8, we have cosine of 3z. And then we have sine raised to 10, sine of 3z raised to 10 dz. So, we know that we can let u the sine. Why? Because if we get the derivative of sine, this will result to cosine. So, in order for us to really understand first, okay, or to realize what will be our u is to rewrite this first as, this is the same as rewriting as sine of 3z, okay, raised to 10 dz. Okay, these two are the same. So if we are going to let u as sine of 3z, okay, so what will happen here? What will happen here is to get the du of this with respect to z, of course. So, of course, we get cosine of 3z and then differentiate the inside function of the sine that with respect to z, that would be 3. And we have dz. So, we have du equals 3 cosine of 3z dz, of which we have a present cosine 3z multiplied by dz here. All we have to do is to get this one, okay, to isolate cosine 3z dz by dividing both sides by 3. So we have d all over 3. We have cosine of 3z dz in here. So now we can substitute. U-substitution. So we have integral of, okay, first one, sine of 3z. That is our u. Don't forget, this is raised to 10. And of course, we have cosine 3z dz, which is equal to du all over 3. Okay? Du all over 3. So, what happens here is that we can factor out 1/3. And then we have u raised to 10 of du. It's very easy. Okay, by power rule, we have u raised to 11 over 11 plus c. Then we have 1 all over 33 u raised to 11 plus c. And we need to substitute u back to its original, again, variable. So we have 1 all over 33. And then u raised to 11, u is sine of 3z raised to 11 plus c. So this should be our answer, or we can you can express this also in 1 over 33, okay, sine raised to 11 of 3j plus c. So we can get the answer here. Okay, let's go now to problem 9. Okay, problem number 9. So we have secant squared of 40. Then we have quantity multiplied by 3 minus tangent of 40 cube, okay, dt. So it's pretty much the same with the problems that we have encountered. So we have a present trigonometric function tangent and secant. We know that the derivative of tangent is secant squared for secant squared. So there is a great chance that we can choose, or our choosing of u will be right if we choose this term, okay, including the tangent. Well, of course, including the 3 also. So let's get u as 3 minus tangent of 4t. Okay? 3 minus tangent of 40. Differentiate this with respect to t. So we have 0 minus, okay? The derivative of tangent is secant for t, okay? And differentiate also the inside function of tangent, which is actually 4 with respect to t. Okay, review your differential calculus if you have forgotten on how to differentiate, or view my videos about that. So we have du. So this would be negative 4 secant. So oops, this would be secant squared. Secant squared 4t dt. And we know that secant squared 40 dt is present. So we have to isolate this secant squared 40 dt on the right side of the equation by dividing this into negative 4. So we have du raised to negative 4. Then we have secant squared 4t. We have dt. So, and then we can now substitute this. Okay. Write this first. 3 minus tangent 40. That would be our u. U raised to 3. And of course, our secant squared 40 dt is equal to du all over negative 4. So that we can factor out negative 1/4 outside of the integral sign. So we have u cubed du here. So this is power rule. So we have negative 1/4. Okay, u raised to 4 all over 4 plus c. So we have negative 1/4. Okay, or negative 1 all over 16, I mean, because 4 multiplied by 4 would be negative. Okay, that's negative because of this negative. So negative 1 all over 16 of the u raised to 4 plus c. And again, what are we going to do? We substitute it back to its original variable t. So u equals 3 minus tangent of 4t raised to 4 plus c. So this should be our final answer for this problem. Okay? And for our last problem for this video, the integral of secant squared v, okay, e raised to 1 plus of tangent of v dv. So it can look so complicated, but it's not. Okay, as I've said, we only have to choose one u here. So since we have secant squared v here, we have tangent here, it's very obvious that I could choose this as our u. 1 plus tangent of v. Differentiate that. That would be 0 plus secant squared of v dv, which is actually secant squared of v dv is present here. Okay? So it is very simple. We can now substitute it. So we have the integral of e, okay, this e, raised to 1 plus tangent of v, which is, we labeled it as u. And then, of course, the remaining factor, secant squared v and dv, will now be our du. Okay? It's only equal to du. So integrate this. This should be e raised to u. plus c. But we know that u equals 1 plus tangent of v. So we have e raised to 1 plus tangent of v plus c. And this would be our final answer. So, thank you so much, guys, for listening. I hope you learned something about our lesson, all about the integration by U substitution. Again, thank you so much for listening. Again, this is Engineer Abat. See you on the next video.